Okay, so thank you to the organizers for giving me the opportunity to talk to you about this. So what I want to do is give an overview and a sort of historical narrative about the ideas that go into sort of recent work on looking at a view of algebraic K-theory as a functor from some kind of homotopical category of certain homotopical categories to spectra. And the story I want to tell is both sort of a story of high technology in terms of trying to figure out ways to make sense of this side of the board. And this is where the higher categories or infinity categorical language will come into this. But it's also a sort of long historical story about things that have been ideas that have been in algebraic K-theory for a long time. And I want to give you a sense of that also. I'll try to start at the beginning, or some kind of beginning. And for us, the beginning is Waldhausen. So Waldhausen explained how to make K-theory out of what we now call a Waldhausen category. And this is a category C. It's a small category with distinguished subcategories WC of weak equivalences and CoFC of cofibrations. And I'll tend to draw these using sort of standard decorations. And these, so you have a small category, you have these subcategories, but the important part is that these satisfy some axioms, of course. And so what are the axioms? Well, 0 is that all the isos are in CoFC and the weak equivalences. That's not very interesting. Perhaps more interesting, I should say, so this is C is small and C is pointed. So we have a distinguished 0 object. And one thing we ask is that the map, the unique map from the 0 object to any object, be a cofibration. Yes? Yeah. I might encourage you to think of that as a disability. And I mean, I'll try to write a little bit bigger, but
we could get an assistant next to you.
Yeah. Yeah. No. I'm sorry. That wasn't. Anyway, yeah. I'll try to. Let me say that differently. I'll try to write larger. Okay. So all the initial maps are cofibrations. 2, and perhaps more importantly, is this okay? So if we have a map along a cofibration, and we have any other map, then we require that the pushout exist. And moreover, that the canonical map from Z into that pushout be a cofibration. And 3, so far we've talked about structures coming from the cofibrations, but I want to tell you about the weak equivalences. 3, we require that if I have 2 diagrams of this sort, so I have Z coming from X to Y. That got small again. Sorry. No semantic content is to be imputed by the different sizes here. So if we have two cubes, right, then and we have vertical maps, and these vertical maps are weak equivalences, then that implies that the induced map on the pushout is itself a weak equivalence. Okay, so the question now to contemplate is, what is this telling you? And I'll answer this question. So what this is telling you, this is a presentation of a homotopical category. Right? It's a category with weak equivalences, so you can make sense of the homotopy category. And it's a category where I've distinguished some squares as being homotopy pushouts. Right? That's what this data is telling us. So we have pushouts, but these pushouts are invariant in the weak equivalences. So this is a category C with weak equivalences. So we can make sense of HOC, but it also has a distinguished collection of homotopy pushouts. And let me emphasize there are a couple homotopy pushouts of particular interest, or classes of pushouts of particular interest. So one thing this says is that if this is a cofibration, we can always take the pushout along the map to the terminal object, and this is a homotopy cofiber sequence. So one way of looking at what this data is doing is it's telling us which maps have homotopy cofibers. Okay? So this, we're specifying which maps have. As a parenthetical remark, I'll also point out, and I'm not going to do anything with this, but let me mention it for cultural context. So we also, of course, always have the pushout that looks like this. And this is the coproduct of x and y. And this makes our category C into a symmetric monoidal category with a co-Cartesian model, symmetric monoidal structure. And so if you are interested in forms of K-theory that come from symmetric monoidal structures, which we won't say very much about, you can connect to that story using this structure. And there are things to say there, but I won't. OK, so we have this homotopical data. And now, let me see what else I wanted to say. Oh, I want to say one thing. I want you to think of this as an exact sequence. I mean, you're probably used to thinking of cofiber sequences as exact sequences anyway, but let me explicitly introduce that language now. We will come back to that idea repeatedly. And from this, so what do we do with this? Well, Waldhausen tells us now how to build algebraic K-theory from this data. And so I'll tell you a little bit about how to do that, although not too much. So Waldhausen defines a simplicial category out of this data where Sn of C is a subcategory of the functors from the arrow category on N, which I think of as the ordered set, to C. And what this looks like is, so this is, the objects are pairs ij, where 0 is less than ij is less than or equal to n. And they're maps from ij to I prime, j prime, if I is less than I prime and j is less than or equal to j prime. And it's not all of those functors. It's a distinguished collection of them. And so let's say which ones. So it's, in particular, we want, so these look like collections that I'll write aij. And we want to stipulate that aii.
So your arrow category here, sorry, the objects are all pairs?
Well, subject to this condition. Yeah, sorry, thank you. I is less than or equal to j.
Okay, cool.
Sorry about that. OK, so we want aii is equal to a point for all I. I want that the maps aij to aik for I, j less than or equal to k. I want these maps to be cofibrations. And I want the squares aij to aik to ajk. And this goes to ajj, which is equal to a point. So I want this to be a homotopy cofiber sequence. So we have these three conditions. And the set of these things is SNC in a way that I'm not going to describe in the interest of time. These fit together into a simplicial structure as n varies. And so we have, so S dot of C is a simplicial, and in fact, a simplicial Waldhausen category. And Waldhausen tells us, and I'm speeding through the definition of algebraic K-theory because, as you'll see, we don't actually need to know the precise details for most of the rest of what I want to say. But in the interest of completeness, I'll just point out that now what you do is you take the nerve of the weak equivalences. So the weak equivalences in this diagram category are pointwise. The cofibrations are more complicated, but the weak equivalences are pointwise. And I take the nerve of those, and I take the diagonal of that in a geometric realization, and I take loops on that, and that's the K-theory space. But let's not worry about that. Let me point out, however, that, and let's see what I wanted to say. So at this point, what I want to observe is that we can relax the data a little bit. So I talked about cofibrations and and push-outs along cofibrations as a model for homotopy co-Cartesian squares. But one thing you might imagine doing is thinking about a K-theory where all you kept track of, or maybe not all, but much of what you kept track of was just which maps have homotopy cofibers and which squares are homotopy co-Cartesian. And you can make sense of this. There are lots of ways to make sense of this. I want to tell you about one particular way of doing it. And this piece of things is from a paper I wrote with Mike, or series of papers I wrote with Mike Mandel. And the idea is that we'll make a definition, which is that we'll say that a map x to y is a weak cofibration if it's equivalent via zigzag in the arrow category to an actual cofibration. And I'll say that a square x to y to w to z, a commuting square, is a homotopy co-Cartesian square if it's equivalent via zigzag to an actual push-out. Let's get the letters right. Along a cofibration. OK? And if you think about it, I shouldn't push this up at all, I'm sorry. If you think about it, these things, so when can you make sense of these things? If you have a cylinder, right, if you have functorial factorization, then you can make sense of these notions, and they act the way you expect them to. A priori, you might worry, is the composite of two weak cofibrations a weak cofibration, for instance? And that's not always true in a generic Waldhausen category, but under any sort of reasonable conditions on the homotopy category, so a homotopy calculus of fractions or something like that, then this works out fine. So, or 2 out of 6, and the weak equivalences are closed under a retract, or these sorts of things that come up. And now when you have this, you can make the following definition. You can say that you can define the S prime dot C construction, which is the same as the S dot construction, except now I require that the initial map to AII be an equivalence. So AII is weakly equivalent to a point. And AIJ to AIK is a weak cofibration. And AIJ to AIK to AJK down to A, that this be homotopy co-Cartesian. Okay? So I've weakened all the conditions to be these sort of up to these homotopical notions more explicitly. And what's good about this, and the reason that I'm telling this part of the story in this way, is this makes it evident what the sort of right functoriality is for algebraic K-theory. Right? Algebraic K-theory, I haven't said anything about this, but algebraic K-theory is functorial in functors that preserve the structure of a Waldhausen category. But in this particular case, what that means is that the S prime dot of C version of K-theory, which is equivalent to the usual one, is functorial in what you might call weakly exact functors, which means these are homotopical functors. They preserve weak equivalences and the point up to weak equivalence, and they preserve homotopy co-Cartesian squares. Okay, so now what this suggests, so what this is supposed to indicate, what this does indicate, maybe not supposed to, is that algebraic K-theory is an invariant of what for now I'll call the underlying homotopy theory of C. Right? It's about homotopical data presented by C. And this might lead to some questions. Right? You can ask, and there's sort of weak and strong forms of these questions. But let me tell you what the questions are before talking about that. So supposing I have an exact functor, or a weakly exact functor f from C to D. I can ask, when does this induce an equivalence on K-theory? When is Kf from Kc to Kd an equivalence? That's a very natural question in this context. And one thing you might hope, the sort of most naive hope, perhaps, is that, if ho C to ho D is an equivalence, right? And there's a weaker form of this, which is to ask, supposing I have two Waldhausen categories with abstractly isomorphic or abstractly equivalent homotopy categories, do they have the same K-theory? And this is a long and sort of tortured history. The answer is no to the stronger form. And this came up in Brooks' talk, actually. These examples of the failure of Morita theory, maybe originally due to Schlichting and then appearing in work of Duggar and Shipley, tell you that the strong form of this isn't true. But this form actually is true sometimes. So Thomason and Trobaugh, and this paper will come up over and over again, or at least maybe once more. Thomason and Trobaugh show that this is true in the presence of stability. So far we have sort of a generic homotopy theory, but in fact, and I'll explain this in more detail a little bit later, K-theory is a functor, under mild hypotheses, it's reasonable to think of K-theory as a functor of stable categories. And under stability hypotheses, and they work with what you might call DG Waldhausen categories. So their Waldhausen categories have a compatible differential graded enrichment and have the property that homotopy pushouts and homotopy pullbacks coincide, and some other things which I'm not going to write down. But they show that in that case, this is actually true, that it's enough to have a functor inducing an equivalence on homotopy categories. More generally, you can pose a more sophisticated version of this question in terms of the Dwyer-Kahn simplicial localization. So you might ask, version 2, what if f induces, or let's write this as if LF from LC to LD is a Dwyer-Kahn equivalence of simplicial categories. And I'm not going to define the Dwyer-Kahn simplicial localization, but there's a very beautiful observation of Dwyer and Kahn from the 80s, which is that if you have a category with weak equivalences, that's actually enough data to define derived mapping spaces. And moreover, in something that we have no right to expect in this life, those mapping spaces compose on the nose. It's an honest simplicial category, which is a miracle. It really is. And so what this is, just to give you some context, if you haven't seen this, one way to think of this is if C started life as a model category, then LC from X to Y, this is, let's say, a simplicial model category. Then LC from X to Y is, in fact, the same thing as the maps from a cofibrant-fibrant replacement of X to a cofibrant-fibrant replacement of Y. Right? This captures the derived mapping space. If you didn't, you can say much stronger things than this, but this is an easy thing for me to write on the board. And one thing to note is that this object knows about the weak equivalences, and it also knows about the homotopy limits and colimits. You can detect them by mapping into and out of test objects. So this knows all there is to know about the homotopy theory, insofar as we care about it. And you can ask that question, and in fact, that's also true. So there's a series of interesting work here. So there's work of Cohen and Vizzosi, which says that not only is that true, but if LC and LD are abstractly equivalent, then KC is equivalent to KD. And there's work of Szynski and work of mine with Mike Mandel. And what Szynski proves sort of the same theorem and relates it to Waldhausen's approximation theorem. And what Mike and I do is explicitly describe the reason this theorem is true is that K-theory is built from the Dwyer-Kahn simplicial localization. Let me just mention what this is. What you can show is that Sn of C is the total space of a fibration. And the base is some coproduct of homotopy automorphism spaces. Those are the automorphisms in the Dwyer-Kahn simplicial localization. And the fibers look like products of Dwyer-Kahn mapping spaces. And in this presentation, I might add, if you know anything about sort of the explicit models of Siegel categories, this looks very reminiscent of that, and it should. And that's maybe sort of a good segue to the next point, which is that what this is saying, the way to interpret this, I think, now, is that algebraic K-theory is an invariant of the underlying infinity category of C. Okay, and I mean by infinity category, I'm going to mean here infinity 1 category, but I'll be sloppy about that. And you can say something precise. What's the base of that fibration? Oh, I'm sorry. It's the coproduct of homotopy automorphisms of objects. Yeah, or this is of sort of n tuples of objects if you're doing Sn of C. And this is an invariant of the underlying infinity category, because how might you get the underlying infinity category? Well, certainly you could produce it by taking, the homotopy coherent. If you wanted a quasi-category, you could take the homotopy coherent nerve of a fibrant replacement as a simplicial category of the Dwyer-Kahn simplicial localization. And what we've just shown is effectively that this is the thing that controls the algebraic K-theory. And in particular, it's not just an invariant, right? The point of that initial digression about weakly exact functors, in addition to local color, was that it's really functorial in functors on the underlying infinity category. That's what the weakly exact functor is, right? So it's functorial at this level. Okay. This thing?
The underlying infinity.
It doesn't. It has. So I'll say something slightly more detailed about, well, not much more detail, so maybe I'll say this now. So it doesn't. The proof by intimidation. No, the point is that you can, by rigidification results for diagrams, you can prove that homotopy colimits in the infinity category can be rigidified to homotopy colimits in the Waldhausen category. And so those things line up. It's true.
Like, what if I chose for my cofibrations just only the isomorphisms?
Well, then you would get, then you would get something sort of, that would be reflected in, if you set that up so it was a Waldhausen category, that would be reflected in the Dwyer-Kahn simplicial localization, and you would get a less interesting algebraic K-theory. Or maybe it was just the algebraic K-theory you wanted. But those choices propagate through. And I can say more in detail about this perhaps after the talk. But so, okay. And I think, right. So, all right. So that brings us to the end of the first half of the talk, which was to set up the following question, the point of which was to set up the following question. And that is maybe two questions. One, what kind of functor is K-theory? So it's some homotopical functor from, it preserves DK equivalences from some subcategory of small infinity categories to spectra. But can we say anything more about characterizing it? And two, can we build K-theory directly from, let's say, infinity categorical data? And the answer to both of these questions will be yes. One thing I'll mention in passing, well, yeah, the answer to this question might not be yes, but maybe it'll be we can give a characterization that's emotionally satisfying. And the answer to question 2 will be yes. One thing to say for those of you who care about these things, that if you think, you might wonder, if you look at this, you might wonder, can I realize this particular model, can I realize the simplicial structure maps here? And the answer is no, for interesting reasons. So this is something you really, and what happens is basically a coherence problem arises. And of course, that's part of what this higher categorical technology is about dealing with in cleaner ways. OK, so let me motivate the kinds of answers now that one can give to these questions. And now I'm going to give sort of more prehistory in a sense. So there's a slogan which is sort of relevant for the remainder of the talk. And the slogan is that, what I said at the beginning is algebraic K-theory is about encoding the homotopy theory of a presentation of an infinity category. But a better slogan for the second part of the talk is that algebraic K-theory splits exact sequences. Okay? And that's the salient property that we want to focus on at this juncture. So in the case of, this is an old fact, right? You know this. Or if you know what K0 is, right? The Grothendieck group of a Waldhausen category is defined so that this is true, right? How is this defined? This is the free abelian group on weak equivalence classes of objects modulo the relation that if I have a cofiber sequence, then I have an equation in the group x plus y mod x is equal to y. And what has this done? Right? What this says is that I can't tell the difference between, I can't tell the difference between this sequence and this sequence. Right? In the Grothendieck group, there's no distinction between the data supplied by the trivial split exact sequence and by some potentially non-split exact sequence. These give rise to the same equation. Same in K0. So you can wonder, how does this manifest in higher algebraic K-theory? And this brings us to sort of one of the central theorems of Waldhausen, which is the additivity theorem. And what this says is, this. But let me tell you how it says it. So remember, we had this thing Sn. And in particular, I should have, and I intended to write out the example of S2 earlier, but I'll do that now. What does S2 of C look like for C, a Waldhausen category? Well, it looks like here's a point. And that maps into, that's A00 into A01 into A02. And now, down here, I have another point, and this maps to A12. And I required that that was a push-out. OK, so what am I writing? This is the category of cofiber sequences. Right? And maps are natural transformations. So this is the category of exact sequences in C. And what Waldhausen proved was that let's find other chalk. OK, so what Waldhausen proved was the following, that K-theory of S2 of C, that's a perfectly good Waldhausen category, is equivalent to the K-theory of C cross the K-theory of C. And what's the map that does that? It's the map that takes the sequence A to B mod A to the pair A and B mod A. And this is split, it turns out, by, or there's a homotopy inverse given by the thing that takes that pair back to A plus B mod A to B mod A. OK? So this is, a precise analog of this kind of picture. Now, what's interesting about the additivity theorem is that if you've read 1126, so if you've read Waldhausen's masterwork on algebraic K-theory, he derives everything, basically, from the additivity theorem. Maybe not the sphere theorem, for those of you who know that, but almost everything else. So Waldhausen derives almost everything else we know about K-theory from the additivity theorem. Moreover, there's very beautiful work of Staffelt and Mccarthy, which is relevant to mention here. So Staffelt showed that if you think about Quillen's K-theory for exact categories, an exact category is an example of a Waldhausen category and is subsumed into this context. And if you think of what Staffelt showed was that Quillen's theorems, Quillen proved a bunch of reduction theorems about algebraic K-theory, and all of those come from the additivity theorem. He deduced all of them. This was building on earlier work of Grayson. Now, most of Quillen's theorem, not the Devisage theorem, interestingly, but most of the rest of Quillen's theorems come from the additivity theorem. And now Randy Mccarthy did something magic. And so what Randy did was there's a school of enterprise of giving better and better proofs of the additivity theorem. And one of the first, and this is genuinely useful, and maybe I'll motivate that by talking about Randy's, which is a nice one. So Randy Mccarthy gave a proof of the additivity theorem where he proved it by writing down an explicit simplicial homotopy. His proof is 1 page long. The paper is 4 because he needed to have a bibliography and a header. But it's mostly just typographical issues with describing what the simplicial homotopy is. And so Mccarthy, let me write this. He proved the additivity theorem via... Yes, but he proved something stronger, which I'm about to state. But yes, that's what I mean by the additivity theorem. Via an explicit simplicial homotopy. And what he really proved was, as I was saying, was something stronger. And there's a nice section in the Hesselholt-Madsen Annals paper that John Rognus mentioned, where they resolved the Quillen-Lichtenbaum conjectures, or some of them. There's a nice discussion of how McCarthy's arguments work very broadly. And this was also in McCarthy's thesis. So these work very broadly. And what I mean by that is something precise, namely, so suppose that F now is a functor from categories, small categories, with cofibrations to spaces. And suppose F is reasonable. And by reasonable, I'll mean that F takes F of a point, F of the trivial category is equivalent to the point, and F preserves up to equivalence Cartesian products. And F has the following sort of niceness property with regard to simplicial objects. So if you apply F, you can form a functor where C is a simplicial category with cofibrations. You can apply F level-wise and take the geometric realization. And I require that if F of Cn to F of Dn is an equivalence for all n, then that induces an equivalence on realizations. Okay, so I have control on the behavior of this thing after geometric realization. If these things are true under these hypotheses, then Randy shows the argument shows that the functor f of s dot of blank geometrically realized. So this is now another functor from from categories with cofibrations to spaces. That this functor has the additivity theorem. So what is this saying? This is saying something interesting, which is that the S dot construction is in some sense a universal construction for forcing a functor to be additive. Right? That's what this tells you, is that S dot is the universal way to force a functor to be additive. Now, I should say that Hesselholt and Madsen, their enterprise here was to work out the details of what this implies about things like localization sequences in an arbitrary theory. They were interested in topological Hochschild homology and cyclic homology. And the story is slightly more subtle, particularly for localization, than I'm letting on. But nonetheless, basically what this says is that any functor that you make this way has the properties of algebraic K-theory. OK, so at this point, well, let's see what happens at this point. So now I want to make this precise in a different way. So I want to use this insight to pick out what kind of functor algebraic K-theory is as a functor out of infinity categories. Okay, and there are two schools of thought on doing this. Let me explain what we want. We're going to characterize algebraic K-theory in terms of what I'll call additive functors on certain infinity categories. And I'll pause for a second and explain. Let me explain why we do it this way. So one of the things, there are lots of good things you get technically from having a good theory of infinity 1 categories around. And one of them is having a homotopical category of infinity categories and having functor categories. Right? You may know that these are classically problems when working with things like model categories. And that's what we're using this for here, and you'll see this. So we can characterize algebraic K-theory in terms of additive functors on infinity categories, and there's sort of two, maybe I'll write these two things over here. There are two approaches to this that I want to describe in accelerated sketch form. So one of them is due to Clark-Barwick. And the idea here is that what do you take as your starting point? You start with what we'll call, well, what he calls Waldhausen infinity categories. And a Waldhausen infinity category is supposed to be an infinity 1 category that has a distinguished class of maps with cofibers and distinguished pushouts that satisfy the axioms you would expect. Okay? As an exercise, you could write down the definition of what this is supposed to be. But there's another starting point, which sort of originated in Gonzalo Taboada's thesis and was worked out in this context by me and David Gepner and Taboada. And here the starting point is a little bit different.